Hello everybody. This video is going to be the first of a three-part short series of videos where we'll discuss how we can take a problem in a context, a word problem, and view it as an arithmetic sequence or a geometric sequence, and basically how we will spot those sequences living in a block of text and treat it accordingly. But so let's get started on the first one here, and this is sort of a lot of text to read. You have to take your time, go over it carefully, and make sure you understand what you're being asked. Oh, wrong page. But anyway, here we go. So this is 1.4, Applications of Arithmetic and Geometric Sequences. This is in the notes that are posted, and so I'm going to get started reading this, okay? It says, Mr. and Mrs. Gloop want their son, Augustus, to do his homework every day. Augustus loves to eat candy, so his parents have decided to motivate him to do his homework by giving him candies for each day that his homework is complete. Mr. Gloop says that on the first day that Augustus turns in his homework, he'll give him 10 candies. On the second day, he promises to give 20 candies, and on the third day, he'll give 30 candies, and so on. All right, we're reading this text here. We haven't been asked a question, but we do see a sequence living in here. All right, so what I want you to think of as you read this, the language being used here is the first day 10 candies, second day 20, third day 30. This is setting us up for a sequence. Now, and when we think of it that way, it sort of already organizes our thoughts a little bit, where it's not just all that text can be blurring, right? So we're going to say, okay, the first day was 10, the second day was 20, the third day was 30, and so on, it says. Now you can think of these days as your ends, right? N is 1, 2, 3, and go from there. All right, so if you're looking at this pattern of numbers, we've been trained, or at least we are starting to learn, that this can be treated as an arithmetic sequence. It's not telling me in the text that it is, but when you look at the pattern of numbers, your experiences that you've worked with so far should let you realize that this is changing as a plus 10, right? This is a D equals 10 common difference. All right, so let's come back in here and see if they're asking me some questions about this thing. All right, it says, here's the first question. Write an explicit formula that shows the number of candies that Augustus earns on any given day with his father's plan. Okay, so that's sort of what we already started working on there. So let's clean this up and go at it here with an explicit formula. So you could use A sub n, or you can use F of n. You know what, to mix things up, I think I'll use A sub n. So A sub n is arithmetic, so we need the first term. Let me just write the formula out to show you what I'm doing. I'm going to use this formula right here. Okay? All right, so I'm going to plug in what I know. A sub 1 is 10. Common difference is also 10. And we get n minus 1. Now, cleaning this up, we get A sub n is equal to 10. All right, hold on now. 10n minus 10. So that's just going to leave me 10n, right? This one really cleans up nice, because this would become, just so you can see what happened here, this is 10 plus 10n minus 10. So those guys are going to cancel each other out just to get you 10n. All right. Okay, so that's our explicit formula part they wanted. Let's see what else they say. Use the formula to find how many candies Augustus will get on the 30th day of his plan. So that's what we built this formula to do. Remember, I said this a long time ago, or several videos back. You build these formulas to do a job. This formula does is to predict the number of candies within this particular context. So let's use it to do that. So what they're saying is how many on day 30. So what you want is A sub 30, right? And that is 10 times 30 Somebody might have said, Mr. Ellis, I could have brute forced come up with that answer, and you probably could have, honestly. This is a pretty simple one, but not every good example has to be complicated. Sometimes a simple example gets the point across even more. So this is what we would use to make that prediction, and I'll fill the notes in after these videos. So when you're looking at them, I'll have them filled in. Okay, let's summarize for a minute here. And this isn't really that mind-bogglingly brilliant stuff I wrote here. It's just a couple of guidelines. It says modeling a linear progression. Folks, arithmetic sequences are a linear progression. All that y equals mx plus b stuff you've learned in the 8th grade and all these functions and this function notation, if it's arithmetic, it is linear. Recall that an arithmetic sequence is a linear progression. That is, it changes at a constant rate called the common difference. Carefully read the text and write the first few terms. That's my advice to you guys. So when you're reading this text, you want to spot language like each day. And those are your ends, right? It's going up day by day by day. And write the terms that discusses their changes. Positively identify the sequence as arithmetic or geometric. See, in the next video, we start dealing with geometric as well. And when you get a problem set, they're going to be mixed together. So you're going to have to positively identify the sequence. And you do that by writing the first few terms, okay? Or at least that's a good way to get at it. So in terms of notes for this section, I think I left a little note in the box that all you really need to do is copy down this box right here. And you might write down the problem I solved. This will always be linked if you need it, so you can see how we did it. So anyway, I'll see you in the next video. We'll talk geometric, okay?